Welcome to Operating Systems Lecture 9. Right, so far we have seen operating system abstractions, typical operating system abstractions. A process has its own private address space. All of the processes, code, data, stack and heap live in that address space, right? And depending on what are the values of certain registers like EIP, ESP, etc., you know where the code is, where the stack, etc., what to execute next. The OS transfers control of the CPU to a process, and then the process is free to run. Right, so the OS is completely out of the picture when the process is running, in some sense. The OS can regain control if the process makes a system call, for example, right? It causes an exception, like a divide by zero or a segmentation fault, or some external interrupt occurs, like some device needs attention, in which case, you know, the OS comes into play, right? So we all understand it so far. Then we also said, you know, to implement address spaces, there is a mechanism called segmentation, which involves on-chip structures like segment selectors, CS, DS, etc. There are segment. So there is a global. There's a descriptor table. So there are segment descriptors. And segment selectors point to segment descriptors, and they live in structures like the global descriptor table, right? And global descriptor table is also pointed to by an on-chip register, like which is called GDTR, right? All right, and so this allows you to implement address spaces, and each process can have a separate base and limit, and completely non-overlapping base and limits will ensure that every process has a private address space. Also, the operating system can have a private address space for itself, and so, you know, and you should make sure that the operating system's base and limit is not overlapping with any of the processes. Okay, then we said, okay, but we also need to implement system calls, etc. So, you know, I need to transition between address spaces and all that. So firstly, the GDT and descriptors also have a field which says whether it can be executed in privileged mode or not. So certain segments are allowed to be executed accessed in only privileged mode, and others are allowed to be accessed in unprivileged and privileged mode, both. Right. And then we said, how do you transfer control? An application, a process shouldn't be just allowed to say that now I want to execute in privileged mode, right? So, but you sometimes want to execute in privileged mode. For example, if you want to make a system call, or there's an interrupt, or there's an exception, etc. So, for that, to facilitate that, we have what are called, you know, interrupt descriptors. And they live in the structure called the interrupt descriptor table, right? So if an interrupt occurs, and I'm using the word interrupt to mean any of the following conditions: exception, system call, or external interrupt. Or the other term for this is traps. So if a trap occurs, the interrupt descriptor dictates how it should be handled, right? So the interrupt descriptor contains things like the CS:EIP pointers, and that's what you transfer to, right? So what the OS, so this is the mechanism provided by the hardware. It's the responsibility of the OS to set up these interrupt descriptors properly, so that if an interrupt occurs, then, you know, the appropriate handler gets called, number one. Number two, the process itself should not be able to override the handler, right? And number three, the handler itself should be very trusted piece of code. It should not have any bugs or anything. Otherwise, you know, an OS, a malicious process could actually trick it to do something which he wants, which the OS shouldn't be really doing, all right? Because if the code segment is a privileged code segment, the handler is going to be executing in a privileged mode, all right? And so the handler has to be very carefully written, so that you know, the process cannot ask the OS to execute his code in privileged mode, for example. Okay, and then we said, look, so on each of these traps there is a user. So trap can happen in a kernel mode, in which case, you know, the old CS and EIP is stored on the current stack, whatever the stack pointer is. Because it was already executing in the kernel mode, the current stack must be something that's trusted. The kernel must have set it up itself. So if a trap occurs in the kernel mode, the old CS and old EIP and old E flags are stored on that stack, right? On the other hand, if a trap occurs in user mode, it's not safe to store these values on the user stack. So what happens is, if a trap occurs in the user mode or the unprivileged mode, the processor also switches the stacks, right? And how does it know where to pick up the stack from? Yeah, there's a data structure, there's a hardware structure called task state segment, which points to the task state segment, and so you can basically pick up so the hardware knows here's where to pick up the stack pointer from, and it loads that stack pointer and then pushes these things onto it, right? So because it's also loading the stack pointer, it also needs to save the old stack pointer, right? So if you take a trap in the user mode, you are saving 5 values to the stack. If you are taking a trap in the kernel mode, you are saving only 3 values to the stack. Okay? All right. So it's the responsibility of the kernel to set up this task state segment appropriately before transferring control to the process, right? Because if it doesn't do that, then if a trap occurs or a system call occurs, then things can go bad. Okay. Now the other thing is that so each process has an address space. Each process also needs to know what is the kernel stack that it's run on, right? So we said that the kernel could be implemented in 2 ways. One is the process model, where one stack per process, one kernel stack per process. In this mode, whenever you transfer control to a process, you have a special area which you call this process's kernel stack, right? Special memory area, and that's basically what you load into the task state segment. So before you actually transfer control to process P1, you load P1's K stack. Before you transfer control to P2, you load P2's K stack, and so on, right? In the other model, which is the interrupt model, you basically say let's just have one stack, right? And so irrespective of whether you transfer to P1 or P2, the stack will be the same, which is one kernel stack. Let's call that the K stack, right? And so basically what that means is that whenever a process actually transitions to kernel mode, it will always start with a completely fresh stack, right? Completely fresh. A fresh stack basically means it has nothing else except the 5 values that were pushed on the trap itself, right? 5 or 3, whatever the case may be. So in the interrupt model, whenever you transition from the user to kernel, typically you will start with a fresh stack, all right? Actually, even in the process model, typically you always start with a fresh stack, but the kernel actually has a flexibility to actually say that, look, these are some values already pushed in the stack, and so in the process model, for example, I could say here is my here is my ESP0, and I could have already pushed some things here, and when the trap occurs, actually the 5 values get pushed here, and so the stack is not completely empty. It also has other stuff which the handler may need, right? But typically this is not used. You also start with a fresh stack in the process mode, right? You don't really have things that are saved previously, and similarly in the interrupt model. Of course, it is possible that while a process was actually executing in the kernel mode, so so now I'm going to use this terminology. A process could be executing in user mode, which means the process is executing in its own address space with its own EIP and all that, or the process could be executing in kernel mode. What I mean by a process executing in kernel mode is, let's say a process executes a system call, I transition to the kernel. It's not the process which is executing, but it's the kernel which is executing on behalf of the process, right? Or there's an interrupt that happened, so it's a kernel. There's an external interrupt that happened, so the kernel actually takes over, and the kernel is executing on the stack that was for example the stack of the process that was originally running, right? So even in this case, I'm going to say that the process is running in the kernel mode. It's really the kernel running on behalf of the process, or in other words, is the kernel running on the stack of the process in the process model, right? Okay.
So in interrupt model, if there is something already on the kernel stack, then it will delete that first.
Right. So yeah, I'm explaining how it works in the interrupt model. So let's say a process was executing in the kernel mode, and now the process wants to switch the stack, right, or switch start another process running. So let's say a process made a system call like read, right, and the file descriptor of the read was actually pointing to a file which lives on disk, and as you know, a disk is actually a very slow device. It's going to take a lot of time, right? So process said read, the kernel figured out that it wants to read from the disk. Now one option is that the kernel could just keep spinning waiting for the disk to complete. That's the polling model. And the other way to do it is you say, okay, I know the disk is going to take a lot of time, so I basically say I want to switch the CPU, right? So I'm going to get the CPU from P1 to P2 while P1's read system call is actually executing on the disk. So P2 can execute on the CPU while P1 is executing on the disk, so to say, right? Now when I'm doing this, when the disk actually completes and I want to get back to P1, then I should know exactly where to start from. In this case, I should start from within the kernel execution, right? Because I was interrupted within the kernel execution and I switched to P2, and now I want to cut back to P1 in the kernel mode, and so the kernel stack should be exactly as it was left before the context switch, right? So this switching from P1 to P2 is also called a context switch, right? And what you need to do in the interrupt model is that when you do a context switch, you also store the contents of the stack somewhere from where they can be restored when the P1 gets context switch back, right, or when it gets restored, right? In the process model, you don't need to save the contents of the stack, you could just save the stack pointer, and that's enough, right? So that's the real difference. There's no fundamental difference. In one case you're storing the contents of the stack if there's a context switch that occurs within the kernel execution. In the other case you're just switching the stack itself. All right, okay. All right, so that's our review of last time's discussion. So I received some questions over email, and there was also a question last time that can't a kernel just jump to the user mode directly using, let's say, the ljump instruction instead of the irate mechanism that we saw last time. So recall that we saw this mechanism where an external interrupt or an exception or a software interrupt enters the kernel after pushing some data on the stack, and then there is this irate instruction that pops this data of the stack and then returns back to the user typically, right? And so I said even the first process, this stack could either be created by an entry to the kernel, by a real entry to the kernel by hardware, or it can be manufactured by the OS kernel itself and simulated, and an irate is simulated as though an interrupt return has happened, although it has not happened, to transfer control back to the user. And so I think the question was, why do I need to do this sort of complicated mechanism where I first set up the stack and then I call irate? Why can't I just do ljump to that particular code segment of the user? Well, it turns out that ljump doesn't allow transitions across privilege levels. Ljump only says selector. Okay, all right. So nothing fundamental, but just a matter of fact. The other question I got was over email was that when you context switch two processes, I said you change the address space, right? So I said that let's say the first sort of dumb way of switching the address space is you change the GDT every time you change the process. So you switch from P1 to P2, you also reload the GDTR each time you do that, right? Before you transfer control to. But we said that's too wasteful. GDT is actually 2 to the power 13, which is pretty big, and if I want to have 1 GDT per process, that's too wasteful. The other way to do that was let's overwrite the values of the GDT itself each time I context switch, right? So each time I context switch, I overwrite the values of GDT and then I can go back. And so the question was, why do I need to even overwrite the values of GDT? Why can't I just have there are 2 to the power 13 entries in the GDT, and so far I've just said there's 6 segments, and so what are the other entries really there for? Why can't I just say process P1 these entries, process P2 these entries, process P3 these entries, and so when I context switch, I don't even overwrite the GDT, I just reload the segment selectors and I'm done. So my GDT contains the segment selectors of all the different processes. When I want to context switch from one process to another, I just change the segment selector. What's the problem?
We can access other processes.
Yes, a process is free to change its segment selector, right? So if the GDT has segment descriptors of other processes, then a process can easily just overwrite its segment selector to point to somebody else's address space. And so that's a security risk. P1 can now access P2's memory, which was not supposed to happen. Right? So you actually need to overwrite the GDT to do that. Sure, question.
Is there a limit to ensure that it doesn't access another process's address space?
Sorry?
We use the limit to, there is a base and a limit.
That's in the descriptor, right?
Yes.
So, okay.
So So while we are changing the CS to point to some other process, it finally gets converted to a physical address which is of some other process. So at that time we are checking the limit also. If it is out of limit, then we should do it.
So let's see how it works, right? Let's say this is my GDT, right? And let's say this was P1 base colon P1 limit, right? And let's say this is P2 base colon P2 limit, right? And let's say this is OS base colon OS limit. This is the kernel's address space, right? All right. Now when I context switch, if I just switch the segment selectors, and a process is allowed to override its own segment selectors. So what all the process needs to do is point to this segment select, right? So P1 can now point to P2, and so that's a problem, right? P1 cannot still point to OS because the OS will have a bit which says privileged, right? So you cannot in an unprivileged mode point to the OS's descriptor, but you can point to another process's descriptor because that's also unprivileged, right? And so you don't want to allow that. So each time you switch between two processes, you actually ensure that the descriptor table GDT has only entries which this process should be allowed to access. Okay.
So technically there is no entry of P2 and GDT when P1 is.
Yes. So there should not be any entry of P2 when P1 is running in the GDT. Okay. So this is the way that that was a suggestion in the question in the email, but this is not how it's done, right? So you won't have separate descriptors for P1 and P2. What you will have is you will have a GDT, right? And you will have something called user base and user limit, and you will have kernel base or OS base and kernel limit, right? So you will have just one descriptor for the process, and each time you context switch, you are going to override this descriptor, all right? That may that may bring you to the question, why do I need 2 to the power 13 entries if that's all I'm using the GDT for? Well, there are other ways to use segmentation hardware, but this is the typical way an OS will use it. For example, this is how Linux would use it, or Windows would use it, or your programming assignment OS PyOS is going to use it, or what we're going to study later, XV6 is going to use it. So most operating systems use this hardware in this way. So hardware designers imagine a certain way of usage. The operating system designers figure out that this is the best way to use it, and so there's some extra things that go into the hardware because the hardware was designed before the OS was written. And even the ring levels are an example of that, right? The hardware designers actually designed 4 ring levels, 0, 1, 2, 3, and the intention there was that you will typically need multiple privilege levels. You will need 0 for the kernel, 1 for the device drivers. This is typically what you hear. Then 2 is for, let's say, the libraries, the system libraries, and then 3 is for the real application, right? So that was the imagination of the hardware designer. The OS designer said, no, I don't need all this. It's too complex. I just need 2 privileged and unprivileged, and so I'm just going to use 0 and 3. Okay. All right. Yeah. So the other question I got was, I refer to the Wikipedia page of GDT, and the GDT has also other things like task statement, LDT, local descriptor table, call gate. What are these for? I would say ignore it. We don't need it for this course. Once again, there are features that are present in the hardware. There's so many features that we are not talking about. All right. There was another question. Sometimes an exception is customized according to a process. So question is, can a process actually customize the exception handler according to itself? So saying that, handle my page fault in this way, or handle my segmentation fault in this way, handle my divide by 0 error in this way, right? Or handle the interrupt from this device in this way, and so on. Can a process do that? Well, in the abstractions we have studied so far, that's not allowed, right? What executes in the kernel on an exception is not controllable by the process. What is controllable by the process is signal handlers. So, for example, Unix provides you this mechanism of converting hardware interrupts or exceptions to software signals, right? So if, for example, you actually did a divide by 0, the hardware is going to generate a floating point exception, the OS's handler for that floating point exception is going to get called. The OS may convert it into a floating point signal and give it to the process which actually executed that offending instruction. And so basically what will happen is that the process which was executing will now straight away jump to the signal handler of the FPE, the floating point exception, right? And so the signal handler of the floating point exception can be customized according to the process. Okay? So the process can customize the handling of at the user level handling. We cannot customize the process, the kernel level handling of a certain condition. Okay, all right. Yes.
So, but how would I tell the interrupt handler to generate that signal?
How will you tell? So Unix basically has standard, certain semantics. For example, a floating point exception will always generate the floating point exception signal, okay, or a segmentation fault will always generate the SIG-SEGV. The segmentation exception on the hardware will always generate a segmentation exception in the signal in the software to the process, right? And there are other ways by which a segmentation signal can be generated, and so on. So there are certain semantics that always an exception at the hardware will generate a signal in the process level. And now the process, and also typically the process will have default handlers for these signals, and the default handler will just say, will just kill you. There are certain signals that can have that can be overridden, the handlers of which can be overridden, and there are certain signals, the handlers to which cannot be overridden for security reasons.
So suppose means there is an interrupt handler and there is a signal handler. In the interrupt handler, I generate a signal. Now I have a set of instructions both in my interrupt handler and my signal handler.
Okay.
Which of these will get executed first?
Okay, the question is, there's an interrupt handler and there's a signal handler. The interrupt handler lives in the OS, the signal handler lives in the process. An interrupt that occurs actually first, what happens? Do both execute, does one execute, etc.? So the answer is that they both execute, right? So when the interrupt occurs, the kernel's interrupt handler gets called. The kernel interrupt handler is the one which is actually going to generate the signal. What does generation of a signal mean? It just means that it's going to override the instruction pointer of the process with the value of the handler. That's all, right? And now it's going to transfer control to the process, just like it was doing earlier. But the only thing is the process is going to feel that it's suddenly jumped from where it was to somewhere else. So that's what generating a signal means. Okay. Yeah, question.
So why is there a need of these two abstractions, interrupt and signal, if all that the interrupt does is generate a signal?
Not always, right? So question is, why do we need two abstractions, interrupt and signal, if all that an interrupt does is generate a signal? So an interrupt, firstly, an interrupt does not always generate a signal, all right? An interrupt could be coming from a hardware device like a disk, and in which case your device driver just needs to just copy the value that's served by the disk to some buffer, in which case you didn't need to generate the signal. So the OS is operating in a different environment, right? The process is operating in a different environment. The question you are asking is, why do I need signals when I have interrupts? The reason is because interrupts cannot be passed directly to the process, because interrupt handling needs to be privileged mode handling, because you are dealing with real devices, real resources, right? On the other hand, you need signals because the process also needs similar kind of event-driven behavior. That something has happened, I want to know about it, and I want to know it in an interrupt-driven fashion, as opposed to keep checking. So Unix signals is not a necessary abstraction. I could just say, I don't need, my operating system does not support signals. If some error condition occurs, if you make an exception, I'll always kill you, right? And if you, for example, make some kind of inter-process communication or some kind of device communication, then it's a responsibility of the process to keep checking rather than a signal-based mechanism. So this is also possible abstraction, in which case an interrupt will not be converted to a signal, right? So just want to, when you're designing an abstraction, you basically want to look at what are the common things and what happens. So and basically what it turns out is that the abstractions that the hardware designers implemented, those are and the abstractions that the operating system designers implemented, there's some similarity between them. Signals are an abstraction that the operating system designers implemented. Interrupts are an abstraction that the hardware designers implemented. All right. So there was another question. Let's say I have a USB port and there are multiple devices connected on the USB port. You can connect a mouse and a keyboard to the same USB port using a hub or whatever. And so now, you know, there's an interrupt, then how does the OS know whether it's a keyboard handler that I should call or the mouse handler that I should call? Well, an interrupt does not just, it just says that all the devices connected to this particular port, or you know, all the devices for which the interrupt vector is this, one of those devices has required my attention. So that's what an interrupt means. Now the interrupt handler will typically now look at all the devices, iterate over them, and check, ask all of them, do you need my attention, do you need my attention, and so on. And if whoever says I need your attention is going to give the attention, and he's going to say what attention you need, right? So interrupt is just a way of telling the processor or that I need attention. It's like, you know, a phone call versus an email, right? A phone call just immediately gives you some attention. You know, when you get a phone call, then you ask, you know, who you are, etc., what do you need, etc. And email is basically, it's in the email box, that's a polling mode, in which case you're going to just check on your own. In both cases, the operation is the same, it's just the way of notification that's different. All right. Okay. Finally, I said that there are two pointers on the chip. There is the global descriptor table register, which points to the GDT, and then there is the interrupt descriptor table register. My question to you is the GDTR, the value in the GDTR, is that a physical address or a virtual address? So what is a virtual address? Virtual address in segmentation is of the form of, you know, percentage some selector, like, you know, CS colon percentage EIP. This is a virtual address, or percentage SS colon percentage ESP, or, you know, DS, EBX, and so on. These are all virtual addresses, right? Or I could say CS colon 100, basically means offset 100 in the segment called CS, right? So GDTR, what does it need to be? Can it be a virtual address, or does it need to be a physical address? Physical address, right? Because I mean, the translation from virtual to physical needs to go through this GDTR, and so if that is a virtual address, then you are in an infinite loop. So that doesn't make sense. In fact, the IDTR also is not a virtual address; it's a physical address. In the terms of what we are saying, you know, when we are only using segmentation. All right. Okay. Okay. So we saw that the process, so basically, so far we have seen that the kernel transfers control to the process. So if I'm a CPU, you know, and this is my timeline. Yeah, give me a second. Okay, question. How does the sorry, how does the what fit in?
How does the physical address fit in the GDTR?
How does the physical address fit in the GDTR? Using the LGDT instruction, right? So LGDT instruction allows you to set up this value. Okay, so it's whatever is the argument to this gets filled into GDTR, operand to the LGDT instruction. Similarly, LIDT instruction fills in IDTR. Load GDT, load IDT, that's what it means. Okay. All right, more questions. In the GDT descriptor, the U base, is it a physical address or a virtual address? Physical, right? I mean, it doesn't make sense. It's a physical address. Limit, it's just it's just a value. It doesn't matter. What about the IDT descriptor? IDT. What does it have? It has a physical address or a virtual address? Virtual. It's basically CS colon EIP, right? So it's basically specifying both the segment and the offset. So it's a virtual address. Okay. Right. So if I look at the CPU and I look at its timeline, basically what happens is, let's say this is boot. So the kernel executes for some time, where it boots up, and then it creates some process internally. So it creates some address space. For example, it creates a segment for the address space, and now it will set up the stack and call iret, and here is the first process that gets run. So it starts executing in user mode. Now this process is going to make some system calls, or, you know, some external interrupt occurs, and so some other kernel activity is going to happen, and then it's going to go return back to user, then it happens kernel, and so on, right? So that's the timeline of a CPU. Sometimes it's executing in kernel mode, sometimes it's executing in user mode, and etc. Now when it's executing in the user mode, it could be executing, let's say, P1 earlier, now it's executing P2, and now it's executing P1 again, and so on, right? and each time the kernel, it switches back to kernel mode, the kernel has a choice whom to get to run next, and he sets things up accordingly and transfers control to that particular process. For example, it sets up the kernel stack, it sets up the address space, and then transfers control to that particular process. So to be able to do this, it needs certain data structures. For example, it needs it needs, let's say, so typically it will have so a kernel will store a list of process control blocks or PCBs, right. So this is basically all the active processes in the system at any time. Now let's say this is boot time. At boot time there is no active process in the system. In fact, during all this duration there is no active process in the system. At this point the kernel, what it does is it sort of manufactures the process. There was no process really at that point, so it manufactures the process. It means it creates a new address space, allocates a new address space, creates corresponding base and limit entries, creates a kernel stack, and adds this process P1's to this list of PCBs. So adds a PCB to this list, right. What does a PCB typically contain? It will contain the ID of the process, PID, all right. It will contain things like state. What is its state? Whether it is currently running, whether it's ready to run but it's not currently running. So things like whether it's running, a process could be actually running right now, right, or whether it's ready to run but not running. So let's call it ready, or let's say it's blocked. Blocked is basically things like I made a request to the disk and I'm blocked, so I'm not eligible to run on the CPU till the disk device comes. Right, so what will happen is the process that made the read system call, that's put in the blocked state. The device is informed that please give me the values of these disk blocks. The device is going to take some time, and after that the device actually invokes an interrupt. The kernel's interrupt handler gets executed. The kernel interrupt handler figures out which request has actually finished. And it figures out that the request that was finished is actually the request that was made by this particular process, and so now at this point it will transition it from block to ready. All right. Okay. So that's state. Now there are other things like address space. For example, what are my base and limits? Right. In segmentation, that's the address space. That's all you need to store. Let's say the kernel stack. If I'm using the process model, then I store only the pointer, or if I'm using the interrupt model, then I store the contents, if any. Okay. And let's say other information. This is just example. We're going to look at what kind of information may be stored, but this is what a PCB stores, right? Where is this list stored? In the kernel's address space, of course, right? You don't want a process to be able to ever read or write to this list. This is completely private to the kernel, and you are implementing this using the kernel's segmentation, the base and limit of the kernel. All right. Now the question is, how does this in what conditions does this transfer happen? We have already seen it can happen through system calls, exception, or interrupt. Now one of the system calls happens to be yield, right? So so for example, Unix will have a system call called yield, and the semantics of the yield system call is that the process figures out that I'm actually waiting for something, and he wants to say that I'm waiting for something and I don't want to take up the CPU. So it's like being a good citizen, and he just says I want to yield the CPU. So he just says I want to yield the CPU. The kernel, you transition to the kernel. So the way it says he wants to yield the CPU is there's a system call called yield. Right? That's the only way a process could communicate with the kernel. So the process says yield, the kernel gets to run, the kernel figures out whether there are other processes who are also waiting for the CPU, and if so, it schedules another process to that CPU. Right? If there are no other processes, then it just says, okay, you are trying to be good, but there's nobody else, so why don't you just take it? All right. Okay. So that's a yield system call. So that's one way that you could transition from user to kernel, in which case you basically transition the state of the process from running to ready. Right? So if actually you if somebody called yield, you basically just transition his state from running to ready, and you transition another process's state from ready to running. All right. But not all processes are good citizens. So there could be a process which just never calls yield. So what do you do? So we've discussed this before. The kernel has has heavy-handed mechanisms, in which case it basically sets up the hardware device called timer. So every computer system will have a device called the timer device on its motherboard, let's say, and so that device is what the kernel has configured before transferring control to the first process. So the kernel has configured the timer device to say periodically generate an interrupt every 100 milliseconds. Right? So even if the process is not calling yield, every 100 milliseconds the kernel's timer interrupt handler will get called. Right? And the timer interrupt handler may do this operation even if the process is not doing it. Right? So a process can be call yield, or the kernel can do it on his behalf. In either case, you are sure that a process cannot run away with the CPU. Okay. All right. Okay. So this mechanism of shifting from one process to another, which is converting my state from running to ready and converting somebody else's state from ready to running, is called a context switch. Right? And of course, it's not just switching states, it also means saving my data, which means my registers, my stack in the PCB. Right? So one of the things that the PCB also contains is, let's say, registers, right? Saved registers. So all these things are saved in the PCB. The state is modified from running to ready. Another process's state is modified from ready to running. Its registers are loaded from its PCB into the hardware state. Stack is set up properly, and you give control, right? And eventually it is going to call irate, which is going to go back to the process. All right. Okay. So this is the timeline of how the kernel executes. All right. So far we have seen that let's say this is my physical address space, and the OS segments it into kernel's area, P1's area, P2's area, and so on. Right. Now, and the kernel internally is storing things like the global descriptor table, the interrupt descriptor table, the list of PCBs, and other data structures that it needs, and also the handlers, all the code that's going inside the handlers. It's all living in this region, right? Now let's look at something which is more fine-grained. Question is, how does the kernel manage this space, right? So this is just a chunk of space that the kernel has reserved for itself. Now how does the kernel manage this space? So typically how a software manages space are using these functions called malloc, which is memory alloc, and free, which is memory free, right? And so what malloc takes is a size and returns a pointer, and what free does is it frees that pointer, right? I'm sure all of you have used malloc and free. Yes? Okay. All right. So, and of course malloc can fail, right? So malloc may return the null pointer, in which case the malloc couldn't happen. And this could happen if you've been mallocing too much and you actually run out of the space that the kernel allocated for itself. Right? So let's see how malloc could be implemented. Typically the way it's implemented is, let's say this is the kernel. So I'm just magnifying this area. So let's say this is the kernel. So the kernel itself will have some code. It will have some data, and it will initialize its own stack somewhere here, right? So these are all the stacks. Let's say. So let's say it's an interrupt-driven model. Let's say it initializes a stack here. So there's only one stack. It initializes it here, all right? And now everything else which remains in the space is what's called the heap, which is managed by these functions called malloc and free. Initially, you just add the entire space to a list called the free list. Right? You add this entire space to the free list. You reserve certain space for the stack, and all the other space you basically say, let's call it in the free list. Each time a function calls malloc, each time the kernel, some part of the kernel calls malloc, you are going to look into the free list, get that amount of chunk of memory, and return it. right? And so on. Each time somebody calls free, you are going to add it back to the free list, right? So you can maintain a list of free memory locations. So let's see how this works. Let's say this is address space, that's the heap, 0 and to some value m, and let's say you mallogged 1, then you mallogged 2, then you mallogged 1 again, then you mallogged 3, and then you said free 2, right? So let's say I said malloc 1, malloc 2, malloc 1 again, let's say, and malloc 3, and let's say my memory allocator is just doing contiguous allocation, just increments the pointer and just gives you the next available memory location. And then I say free 2, right? So what's going to happen is this area is going to get freed and it's going to get added in the free list, and then I say malloc 3 again, and so what happens is this is a region of length 2, you have asked for 3 bytes and I cannot just give you these, right? So because there is no contiguous bytes here, and so what I have to do is I have to go here. And so what can happen eventually is that there can be lots of small holes in your address space, right? So you have areas that have been mallogged and then there are holes in the middle that have been freed, but the holes are actually not big enough to satisfy many of your requests. So eventually your address space will get what's called fragmented, right? This is called fragmentation. So there are many algorithms on choosing where to, when somebody calls malloc, the function malloc has freedom in choosing exactly which area to give, right? And exactly how to manage the space in such a way that you minimize fragmentation is something that we're going to look at later, but we should at least know what the problem is. Okay. Same thing exists in the process level. So I motivated fragmentation in the context of the kernel, but similarly the process has a very similar structure. There's code, there's data, so there's a stack, and now you have the heap everywhere, right? And now the process internally is going to manage its own address space using malloc and free, manage its heap using malloc and free, all right. But when I look at the physical address space again, so let's say this is a physical address space. So this is the kernel. This is P1, this is P2, and so on. And so in a typical execution of the kernel, you are going to see lots of process creations and process exits, right? So process is going to get created, you are going to allocate space for it, and you're going to so let's say P1 got forked, fork P1, then fork P2, then fork P3, then you said exit P1, exit P2, let's say you said fork P4. Right? Once again we have the similar problem. So P1, P2, P3 got created like this, then P2 exited, and now I want to allocate space for P4. Let's say P4 was bigger than P2, I have a hole that I cannot use, and I have to basically use extra memory, right? So there's a fragmentation in the physical address space. What are some possible solutions? Right. So let's say I wanted to look for P4, and let's say I search the entire address space and I couldn't find a block that's big enough for P4. One thing is I can just say fork didn't succeed, I return a negative value to the fork system call. That's one way. But what if the sum of all the holes is bigger than P4? Then can I do something smarter? I can just shift P3 down. What does it mean to shift P3 down? I just change the base and limit appropriately, and the process will never know, right? So this indirection, which is the segmentation hardware, is actually allowing you to move the address space at will inside, and without the process ever knowing, because you just change the base and limit, you move the P3 down, the process code has nothing to do with it, right? Because it sees still the same addresses, 0 to whatever maximum it's allocated. All right. Okay, but it's not a very convincing solution, because a process may be large and copying between memory is an expensive operation, because there are lots of bytes that are going to go over the system bus. You're going to and so because processors are big, copying the entire process is an expensive proposition. Also, let's say I did P1, P2. So let's say I did fork P1, fork P2, fork P3, and then I just wanted to say grow P1, grow P2, by 1 byte. Not possible, because there is P1, there's P3 right above P2, and so if I want to grow P1 by 1 byte, I actually have to find that space, and then I have to copy the entire P2 there, and then I grow it by 1 byte. Once again, very inefficient way of doing things.
So but we are only changing the base value, we are not copying the entire content.
Before you change the base value, but you also copy the physical memory contents, right? You cannot just change the base value, right? Okay. Okay, so so these are problems which are again come what are called fragmentation problems, and the reason they exist is basically because the segmentation hardware allows us to only allocate contiguous regions of physical address space and give them to the process. So I cannot say P2 lives here, 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 and here. So I cannot have lots of different. I cannot just say these are P2's areas, and I cannot just have a list of P2's areas. I just need to say that P2 lives in this contiguous address space. If I were able to say that P2 lives, scattered around in the memory, then it will be much easier. I could just do things in a better way. There is some respite though, because as we said, there are 6 segments. So I could potentially have 6 different contiguous regions, but now the programmer needs to be very careful about which segment it doesn't see a uniform address space. It actually sees segmented address spaces. Oh, this is the code segment, this is a stack segment, this is the data segment. It's possible, but typically you don't use it. Complicates the compiler. It complicates the job of the programmer, or the job of the compiler writer. And so it's not typically done. It's much easier to actually write programs for a uniform address space as opposed to a segmented address space. All right. Okay. So, but that's question. So I think there was a question there.
Sir, you said that when the OS allocates a memory for a process, it doesn't know beforehand how much memory the process needs.
Right.
So shouldn't it do something like the OS should allocate equal memory to all the processes?
Okay. Question. Right. So question is, an OS does not know a priori how much memory a process needs, right? And so question is, shouldn't I allocate equal memory to each process? Yes, I mean that's one way of doing it. I mean, see, what are our abstractions? Our abstractions are fork and exec and things like that, right? And then we have malloc and all that, right? So so when I do fork, I have no idea what this process is going to actually execute, right? So I just I just create an address space. And in segmentation, what I'll do is I'll probably create the address space equal to the parent's address space. But now let's say exec's an executable that requires much bigger memory.
But parent address space cannot increase. You said that if a process tries.
So parent's address space will not increase, but the child's address space may increase, right? Because you called exec, and the executable that you're going to load now is much bigger than the parent's address space. Okay. So I mean, basically the point is that you need dynamic growth of processes, and this way of doing address translation is not supporting very fast way of doing dynamic growth of processes. Question? Okay. Okay, so we're going to look at next lecture another mechanism called paging. All right. So right now, so basically we are really talking about a mechanism in the operating system called virtual memory. And so what is virtual memory? Virtual memory translates an address which is called the virtual address and to a physical address. And there is some function f which does this translation. So far in segmentation, this f was a very simple function where we just said VA is equal to base plus PA is equal to VA, base plus BA, and you also check it against the limit. But what you really need is that this function should be more sort of detailed. So you could be able to say, oh, this byte goes here, and this byte goes here, and this byte goes here. And so what is the most general function? Well, the most general function is for each byte, I basically have something which says, this is where this byte lives, this is where this byte lives. But the data structure to store this mapping will be bigger than the address space itself, right? So what you basically do is you basically divide the virtual address space into what are called pages. And then you have a table in the function which maps one page in the virtual address space to another page space in the physical address space, and we're going to discuss more details in our next lecture. All right. Okay. So let's stop.